Okay, now we're continuing on with multivariate models in our ordination lecture, and we're going to be talking about, for 9.2, we're going to be talking about dissimilarity. And the optional reading for this has to do with a paper that some of the data we're going to talk about in this lecture comes from. It's loosely based on what this paper became. So we were talking about distance matrices, and I want to mention this term called dissimilarity. So as a reminder, we use distance measures, d of jk, to define the distance between 2 points in space, 2 points being j and k. And we used many different ways to calculate these distances, right? So we went over Euclidean distance, Jaccard distance, Canberra, etc. But another way to think about this distance is as dissimilarity. So a distance matrix is a way to represent the difference or dissimilarity between multidimensional sets of data, i.e. 2 rows of data, 2 rows in your data set with multiple y's. So how dissimilar are those 2 rows of data? And so let's revisit our toy example just to make sure that we understand this. So we can take a very short set of data where we have plots 1 through 4, and we have 5 species, A through E, and we have different numbers of those species in each of the 4 plots. So we can create a Bray-Curtis distance matrix or a dissimilarity matrix, and that looks like this. Again, the code is under the hood. We talked about this in the last lecture. And so when you're reading this dissimilarity matrix, you can read it as the difference between plots, the distance between plots 1 and 2, or the dissimilarity between plots 1 and 2 is 0.823. The dissimilarity between plots 1 and 3 is 1, and 1 and 4 is 1, and 2 and 3 is 0.285, and on and on. So here I want to point out that plots 3 and 4 are identical. And so here yij equals yik. So your distance or dissimilarity equals 0. So here you can see that 3 and 4 are the same. And if you look at the toy example at the top, if you look at rows 3 and 4, you see that they are exactly the same. So they are not dissimilar at all. It gets a little bit confusing because of the inverse, right? You want to think similarity. Those are exactly the same, so you'd want to think 1. But we're actually, the way this all works out, we're talking about dissimilarity, so their dissimilarity is 0. So if you look at plots 1 and 3 and 1 and 4, those are completely different. So their dissimilarity is 1. So let's look at 1 and 3 here. So at the top you see there are in 1 there's no species A, D, or E, only B and C. But when you look at 3, you see that there's only A or E, and no B and C. And so as you can see, what species exist in these plots is completely different. And so their dissimilarity is 1, and that's reflected in the Bray-Curtis distance matrix, or dissimilarity matrix. And then it gets more complicated when you get away from 0s and 1s, right? So plots 2 and 3 in our example are more similar to each other than plots 2 and 1. Thus, their dissimilarity is 0.285 versus 0.823. Remember, the larger the number closer to 1, that means the more different plots are. So one cool thing that you can do is use your dissimilarity as a dependent variable. And so you spend a lot of time trying to figure out how different these plots are, but what's one way to analyze it? Though this is one way you can think about things. So one thing that's useful to examine is how different treatments or environmental factors, etc., alter dissimilarity between plots. So you can get interesting data just from this dissimilarity. And so to do this, you need to calculate dissimilarity of communities, and then use this as a single dependent y. So we're moving away from our matrix of y's. We're taking our matrix of y's and creating one value. And this can also be called turnover, because you'll see this in the literature quite a bit, but because you are looking at how species change between plots, for example, a dissimilarity of 1 equals complete turnover, and a dissimilarity of 0 equals no turnover. And so I'm going to demonstrate some work that I did as part of an initial analysis for this paper by Anderson et al. In Ecology in 2018. It didn't end up in the paper, but the method is still useful. So let me remind you of the experimental design. So the question we're asking was how do herbivores and nutrient additions alter community dissimilarity? And so as I've mentioned a couple times so far, the Nutrient Network is this experiment that has the same experimental setup in sites across the world. And so there's 3 blocks within each site, and each block consists of one complete set of experimental plots. And that's down in B. And you can see that in this experiment, we're just looking at full fertilizer addition, so plus NPK or minus NPK, and then with plots with and without herbivores. And so you can see that I've highlighted the 4 plots we're going to be looking at in red. We're not going to be looking at the rest of them. And those little squares represent the sort of black cubes represent an herbivore fence, so how we keep herbivores out. And then to remind you, we have this experiment replicated all over the place, and so we have a bunch of different sites that are doing the same thing, and we want to look at dissimilarity among these communities with these treatments. So what we did was we calculated the dissimilarity using Bray-Curtis and standardized by plot totals for each treatment plot to its control within a block. So we took the entire data set, and here you can see that I have starred the control plot. We have that community, which is a row of data, and then we determine the dissimilarity between that control plot and every other treatment plot within each block. So we look at how different the control is with fertilizer and minus herbivores. We look at the dissimilarity between the control and no fertilizer, no herbivores, and then also with fertilizer and herbivores present. And so there's a lot of code under the hood if you want to see how I did this. You're welcome to look at the code, but I just want to point out that what we get in the end is that for each site, in each block, in each year, we get a dissimilarity from each treatment plot to the control. And of course, this code actually compares each plot to the control, so it eventually compares each control to itself, and so then of course your dissimilarity is 0 because they're completely the same. So we remove those control plots for the analysis, of course. And so here you can see that I just ran a simple mixed effects model where we can now take that dissimilarity, which is a single value for the difference in the community between 2 plots, and see if that's a function of treatment. And then, of course, include some random effects. And I wanted to point out that we've been a little bit confused when we use summary of these models as to what that means. And I recently learned about this really nice function of ANOVA with a capital A, where you can put your model input and specify your test statistics. So here we'd want to use F, and it's in the library CAR. However, I just don't have the right version of CAR. I can't get CAR to install. I think something's going on with my version of R, but I know people have done it because I talked to someone today who used it, so I know it works, so I'll try to get back to you on how to work that. But that should give you, instead of having all of these confusing things where you're comparing one treatment to another, like the NPK treatment to the NPK plus fence, etc., it gives you one output. It's just really nice because you can specify a bunch of different test statistics. You can also use regular old ANOVA with a little a, and that gives you what you're looking for to show that yes, treatments are extremely different. The other one just gives you a little bit nicer of an output. So I just wanted to point that out because I know we've had a little bit of confusion on that in the past. And so here, just wanted to again show you the results of this, what this looks like, what the data look like, right? So we found that treatments are different from each other. And so on the x-axis, we have our treatments of fence. So when you have the fence up, so no herbivores, no fertilizer. NPK, where you have just NPK additions, no fence. And then what happens when you have NPK and your fence up. And again, the dissimilarity on the y-axis is looking at always in comparison to the control plots within a block. So it's one value per treatment per block. And so as you can see in the fence plots, from these box plots, the fence treatments are the most similar to the control, and the NPK plus fence are the most dissimilar because their dissimilarity is a higher number. So those communities are the most different, the most dissimilar from the control. So things are changing more when you add nutrients and you remove the herbivores in the plant community is what this is saying. And with that, please complete quiz 9.2 on Canvas and continue on to the next lecture.